participants already. Shall we start, Pak Nyoman and Professor Ratnaweera? So please please let me open the session first. So good afternoon, everyone in Indonesia, and good morning, Professor Ratnaweera in Norway and Bunopa in London. Sorry, in Southampton. I'm sorry. So first of all, on behalf of the Committee of International Reputation Improvement Program, I would like to express our gratitude to Professor Ratnaweera for kindly accepting our invitation as a visiting professor. This program actually was designed to improve the visibility and reputation of our program study in the international academic and industrial field. So I wish that you will have a good impression after these two sessions and the research discussion in the next year, in the early of next year. So before we listen to Professor Ratnaweera lecture, I would like to invite the head of program study, Pak Nyoman, to open this fruitful event. Pak Nyoman, please, the time is yours.
Okay, thank you, Paraga. Good morning, Prof. Ratnaweera, also Bunopa there, and good afternoon for our student. First of all, of course, on behalf of the Environmental Engineering Study Program, I would like to express thank you very much for Professor Ratnaweera accepting our invitation to help this Studium General. I think this is a very valuable contribution for you, especially to our policy, our program, as Paraga mentioned, part of the widen and heighten the academic reputation program, especially to expose international collaboration. So again, thank you very much, and I believe what you are delivering in this general lecture will be beneficial and add more value for our student, in experience, also lesson to learn about this topic, especially coagulation or population, especially how they can not only know the basic the operational and the process, but also maybe the technology and current issue about these topics. So I think, further we can make such as collaboration again, research collaboration. As you know that our faculty also have International Journal of Technology. So maybe someday, if you don't mind, we can send you invitation as reviewer. Maybe another part of research collaboration. As you know, Paraga or Kunopa already engaged for this cases lecture. So without further ado, I would like to give the times to Prof. Ratnaweera. Thank you very much. And for the student, please listen carefully and make this lecture become good experience and maybe some collaboration for your project, especially your final project, if you have any interest on this lecture. Thank you very much, Paraga.
Thank you very much, Pak Nyoman. Okay, and one thing before we start the lecture session, I would like to remind you, to all students, I would like to remind you that if you have any question, I have made the link to Google Form, so you can type your question there, and then I will read some of your questions in the Q&A session. And also this lecture will be divided into two sessions. The first 45 minutes will be delivered by Professor Ratnaweera, and then we will have 15 minutes break, and then Professor Ratnaweera will continue the lecture session. So the first session will be until about 1:30 p.m. Okay, mohon maaf sekali lagi untuk para mahasiswa dapat I'm sorry I will speak in Indonesian a little bit.
Yeah, sure.
Apabila ada pertanyaan, saya sudah mengirimkan link Google Form. Silakan kalian ketikkan pertanyaan kalian di Google Form tersebut. Kalau dalam bahasa Inggris bagus, kalau dalam bahasa Indonesia nanti akan saya coba translate. Terima kasih. Okay, sorry, Professor Ratnaweera. Now the time is yours. Thank you very much, Pak Nyoman, and we look forward with great anticipation to listen to your lecture. Thank you.
Thank you very much, and good afternoon to all of you in at the University of Indonesia. I'm honored to have this possibility to give this lecture, and also it is my first lecture in Indonesia. Although I have visited Indonesia, I think twice, but I never had any professional activity in Indonesia. But we have started to plan our joint activities. So actually we have applied for 2 projects, and I hope that next year we will have much stronger collaboration. Today I will talk about the chemical coagulation in water and wastewater treatment. Chemical coagulation is the most used treatment process in water supply, and it is also increasingly used in wastewater treatment. So before I start my presentation, I would like to say a few words about myself. I was born in Sri Lanka, and I went to Ukraine, or the former Soviet Union, University in Kiev, to do my master's in chemical engineering. And that was in 1981 to 87. After that, I came to Norway to do my PhD in 1987. So after my PhD, I have been working at the Norwegian Institute for Water Research for 20 years as the Director of Innovation and International Projects. Last 10 years, I have been working on full-time at this university, Norwegian University of Life Sciences. Our university is situated 30 kilometers south of Oslo. Oslo is the capital of Norway. And we have 2 universities in Norway producing masters in water and wastewater engineering. So our university produces about 2/3 of these engineers, and another university in Trondheim produces 1/3. So I have been actively involved in a number of Norwegian and international organizations of water, related to water. So this year, from this year, I'm also an IWA fellow. IWA stands for International Water Association. And I'm also in the Management Council and representing Norway at the European Water Association. So that's briefly about myself, and I am doing lectures in both in Asia, Africa, America, and also a number of European countries through our projects. So we have a network of universities. Right now we have over 60 universities from 44 countries. So they are related with different types of projects. So a lot of international activities, and I hope to welcome University of Indonesia also to this network. Okay, that was the brief introduction. Then I'm going to start the lecture. If you want, you can record the lecture, or shall I record it and send it to you?
We already pressed the lecture, the recording button, Professor.
Ah, all right. Okay,
yeah,
fine.
Thank you.
Yeah. So, coagulation. So, to understand coagulation, why it is important, we also need to know about the particles and colloids in water. So, this picture, this figure shows here, if you're in the, let me see the pointer. Yeah, at the bottom you see the size, like this is 0.1 millimeters, 10 micrometers, 1 micrometer, 0.1, 0.101, and it's 0.1 nanometer. These are the different sizes of particles, right? And here you see what is the size of different types of material. The hair is, that's the smallest thing that we can observe from our eyes, and they are in the range of 10 to 100 micrometers. But most of the pollutants in water, we can't see them. So like bacteria, they are in the range of, let's say, 20, 30 micrometers, and maybe like 500 nano, or around 1 micrometer. So this is the bacteria range. And the viruses are much smaller. They are in the range of, let's say, 10 nanometers to 100 nanometers. Then we have other different solute pollutants like colloids, organic molecules, organic bonds, and different types of things. So if you take the drinking water, if you take the river water or a lake water, so we are talking about in this range, and which means that river and lake water could include bacteria and viruses, which we have to remove during our treatment process. Of course, there are much heavier particles here, like sand and different type of things, and they can be removed without addition of chemicals. So my point here is that if we can remove particles and colloids, we will be removing a majority of pollutants in our water. So why do we have to remove particles? So here I'm presenting two cases. In the blue part, that is the that's about drinking water, water supply, and the yellow part is wastewater. So in drinking water, we need to remove particles to remove the turbidity in tap water, right? So none of us would like to drink water if it is not clean or clear. So we need to remove particles, even though those majority of those particles might not be bringing any threats to our health, but still we don't like to drink that one, right? And if you don't remove particles, then those small particles like sand particles, they might accumulate in the network, create a lot of problems after that. And one of the most important reasons to remove particles is that microorganisms are also particles. So if you have, I'm not sure whether you have learned about disinfection. If not, you will soon learn about disinfection. So disinfection is compulsory activity to provide safe drinking water for consumers. So during the disinfection, there are two processes. We can either remove microorganisms, or we can kill or inactivate microorganisms or pathogen or microorganisms. Killing or inactivating could be achieved by addition of chlorine, ozone, or UV. So chlorine is the most common one. But you can also remove them because they are particles and colloids, and during coagulation or during other types of filtration systems, we can remove that. And particles may also influence the downstream treatment, in particular disinfection, because if we have particles, if we have high turbidity or suspended solids in our treated water, then when we add disinfection like UV, the effect will be reduced. So that's why we have to make sure that all the particles are removed before we start disinfection process. When it comes to the wastewater, then we are talking about completely a different type of water. It has a lot of particles. and fat and grease. So they may cause clogging in settling in pipes and tanks, much more often than in drinking water types. Downstream process will have to remove. So if we do not remove particles at the mechanical or chemical stage, then of course downstream systems like biological treatment have to remove that. And if we have more particles, it could also mean that we have more organic matter as particles. Then we have to have more microorganisms to use biological treatment, which means that we will be using more air and more energy and require more space. And if you have more particles, then we also have to add more coagulants, leading to more sludge. So there are ways to remove particles. So that's why in drinking water plants and wastewater treatment plants, before we add coagulants, we have screens which can remove the bigger particles. So screens could be, and they might have an opening of 1 or 2 millimeters, but there are now advanced screens where the opening could be so small as 0.1 millimeter. So if you have that type of a screen, you will be removing quite a lot of particles. And in drinking water, there is another task. It's not only particles we want to remove, but we also want to remove NOM. NOM stands for natural organic matter. And natural organic matter gives this brownish color in raw water. I'm not sure how serious is this, how often your water sources have this brownish color. And this is especially if you take water from lakes. And these are organic matter which creates this color, and this can create disinfection byproducts when you add chlorine, because chlorine reacts with organic matter and then it generates trihalomethanes, so chloramine. So and that type of disinfection byproducts may cause cancer. That's why we have to make sure that we remove all or as much as possible organic matter in drinking water before we add coagulants. In the wastewater, the other problem is phosphates. They have particles, they don't have organic matter, natural organic matter, they have a lot of organic matter. But we have to remove phosphates from wastewater to avoid eutrophication. That means you have seen some lakes and rivers turn into green, like green soup, right? It's caused by algae. And if we remove phosphates, then we can make sure that the eutrophication will be delayed. Another reason is that world's phosphorus reserves are diminishing. So phosphorus is quite important in our food production. So if we don't have phosphates, then we will have a big problem to produce agricultural products. So traditionally, we have been using mineral phosphates. That means that we dig it out from the ground. But these mineral phosphates are now limited. And it says that within the next 10 to 20 years time, but there will be a crisis of phosphates. So that's why we have to utilize as much as possible phosphates. And in our wastewater, 10 to 20% of phosphorus needs to agriculture is there. So that's why we need to recover phosphates from our wastewater. So more and more countries are now enforcing this rule, saying that you cannot just waste the wastewater. You have to recover phosphates from your wastewater. Okay, now let's look at the processes. Here I'm comparing the mechanical treatment processes and chemical treatment processes. Suspended solids, those are the particles which are larger than 1 micrometer. So usually a mechanical treatment without any chemicals can remove maybe 50 or 60% of particles. COD, organic matter, or BOD, biochemical oxygen demand, could remove about 30%. total phosphorus about 15% and total nitrogen 15%. When you look at these percentages, you understand that today's environmental and health regulations require much higher removals than what mechanical treatment can do. So therefore, we have to consider chemical or biological or a combination. If we have a chemical stage or a coagulation, then we can remove almost everything which we call as suspended solids. So 95%, even 98% of suspended solids can be removed. Organic matter can remove at least 50%, but sometimes even up to 70%. Coagulation cannot remove dissolved organic matter, apart from humus in drinking water, but it can remove all the particulate matter. Total phosphorus can remove almost everything. I will come back to this. And total nitrogen about 30%. So again, now much more simpler version of the first picture which I showed, how the wastewater and wastewater look like. So here are the sizes: 1 micrometer, now 1 micrometer, 1 millimeter, 1 centimeter, 1 micrometer, and 1 nanometer. So suspended solids, those are the particles which are bigger than 1 micrometer. Bacteria are in this range and viruses are in this range. Algae are here and molecules are here. So by coagulation, we can remove everything above this range, like 10 nanometers, or colloids and particles. All the colloids and all the particles can be removed by coagulation. But you can see then all the bacteria could be removed, but not all the viruses, because there are some of the viruses which are smaller than the colloid range, which could be down to 1 nanometer. That's why coagulation alone is not enough to secure the quality, health-related quality of drinking water. So you have to have some disinfection to take care of that part. So in drinking water or water supply, the main objectives of coagulation is to remove particles and remove color. And in wastewater, the main objective is to remove particles and phosphates. So the chemical coagulation process, it's very simply presented here. So when the water or wastewater comes in, first there is a screen to take off the larger particles. In drinking water, it could be leaves, it could be sand, it could be even small fish which are coming through the supply pipe if it is coming from a lake or a river. And then for wastewater, there is a fat and grit chamber. That means it removes the sand and fat. It takes about 20 minutes. And then we add the coagulant, a chemical, and then we mix it slowly to build the flocks. Flocks, these are agglomerates of hydroxides together with other pollutants. And after that, all that goes to a separation stage. It could be a sedimentation, it could be filtration, it could be flotation. So if it is a sedimentation process, it can take, let's say, from 1 to 5 hours. So this is the general description of the coagulation process. Right? And there are 4 mechanisms of particle removal. They are called, as shown here, compression of the double layer, adsorption charge neutralization, bridging, and sweep flock. I'm not going to go into much of details on these mechanisms, but nevertheless, I would like to say a few words about this so that you have an understanding about these mechanisms. First one is to explain the process, what happens in if you take a water with particles. When 2 particles are coming together, there are 2 forces takes place. So these two particles, it could be colloids, it could be bacteria, it could be viruses, or it could be sand particles, right? So when they are coming together, there are two forces. The first one is the repulsion force. Because the particles have the same charge, in water, we say that particles have the negative charge. And when two particles with negative charge comes together, they will retract, there is a repulsion force. If you remember from physics classes from the school, maybe you try to bring the magnets, two magnets, north or positive poles together, two magnets, right? It's very difficult to bring them, and they are repulsing. You can't bring two plus together. The same thing happens when the two particles are coming, so they will not allow particles to come together because they have, both of them have the negative charge. And there is also attractive force. We call it as van der Waals forces, because if two particles are coming together independently of the charge of particles, there is an attraction. So closer they come, higher the attraction power. So these two, the balance or the sum of these two forces decides or defines whether two particles can come together and settle. Right. So in coagulation, our task is to make these particles larger and heavier so that they will settle. So what happens is that here is the distance between two particles or colloids, and this is the repulsive energy, and this is the attractive energy. So if two particles are here, you can say that this is the repulsive energy, and the attractive energy is here, if the particles are here, right? And the sum of these two forces are here. And at this case, the repulsive energy is the balance or the result of these two forces, which means the two particles cannot come together. But if you come somehow, if you manage to come over this, if the particle is so close in here, then suddenly there will be an attractive energy. It means that they can come together. Right? So this is the task of coagulation, which we are trying to do. And how do we achieve that? The first one is a double layer compression. Double layer compression means that in a water solution, particles have the charge. The particle has a negative charge. And because in the solution there are both positive and negative ions, positively charged ions will cover this small particle. This is negative, and these are the positive charge. Right? And because of this charge, there will be a number of other ions also partially attached to this particle. But the difference is that they will be moving with the particle, but they are not firmly attached. So then we are saying it's like a kind of a cloud of particles. So this cloud prevents two particles to come together. But if we add some electrolytes, then we can compress this cloud. So for example, if we add calcium into our water, calcium has the second power of valency, and there's a rule saying, Schulz-Hardy rule, saying that impact of the counter ions will be 6th power of the valency. So by this way, we can simply add seawater, which has calcium and magnesium, and improve the coagulation properties. So this is another way of showing it. So the repulsive energy will be reduced because the diameter of this or diffuse layer will be reduced. The next and the most important mechanism in drinking water is the adsorption charge neutralization. As the word says, particles have negatively charged, and if we can add some positively charged matter, then we can reduce the repulsion between them. And the coagulants, the chemicals which we add, when they react with water and they create positively charged species, and this is why this is what's happening during the coagulation. The third mechanism is called bridging. That happens when we add organic coagulants, organic polymers. And organic polymers have positively charged and they have long chains and they can bind these small particles into bigger like clumps, and then because they are becoming more dense and they can settle. The last one is called sweep flock. Here what's happening is that spontaneous precipitation of aluminium and iron into aluminium hydroxide. So if we add aluminium salt, let's say aluminium chloride, aluminium sulfate into water, if it is within the correct pH, and we will see that water turns into white kind of clouds because the aluminium hydroxide or iron hydroxide precipitation takes place. And when this precipitation takes place, it will also take some of the particles with them and then they settle. So this is the fourth mechanism. So this is an interesting phenomena, and if you wish to learn more about that, there are a lot of literature. I can also provide some links. And there are two other figures which we coagulant, where we are consulting when we are doing coagulation process and studying the process. I'm not going to explain or go into detail with that, but I just want to show that this is the classical figure of coagulation, which shows what happens with the particle concentration and the coagulant dosage. And all the dark shaded area shows that if your particle concentration is here, and if your coagulation dosage is here, then you have coagulation because it's in the shaded part. But if your particle concentration here and the coagulant dosage is here, it is not enough to create the coagulation. So this figure was made by Stum and O'Melia in 1968, so many years ago, but still it is one of the most central figures. The second figure is the so-called coagulation diagram. It was also produced like 40 years ago. And here it shows that the species which are created during coagulation. So this is for aluminium. This is the aluminium concentration and the pH. And here around 6, which means if we want to have the precipitation, maximum precipitation on coagulant, so we have to conduct the test around pH around 6, 6.5 for aluminium, and for iron it is slightly less, around 5.5. So again, I just want to show you these two diagrams, and I'm not going to go into details with that. So that was about the wastewater, but how, and removal of particles, right? And NOM, natural organic matter, how can it be removed? So humic acids, they also have this negative charge. Humic acid, those are the substances which gives color in drinking water. So with coagulants, we add positively charged species. So there is a destabilization or reaction between negative and positive charged species. And then it creates a humic coagulant particle or a flock. And then when they are as bigger particles, then can be removed. In wastewater, we have to remove phosphates. And I said that we can remove almost all the phosphate from wastewater because particulate phosphates will be removed as previous mechanisms as particles. It doesn't matter whether it's phosphates, organic matter, or sand, or whatever. If they are particles, the particles are removed. But the dissolved part, it's not removed so easily. But phosphates, even dissolved, they will be removed because aluminium and iron, which are our main coagulants, they react with phosphates. So if we add aluminium, iron, or calcium into a solution with phosphates, so they will form aluminium phosphates, iron phosphate, or calcium phosphate, or complex of different types, which means they convert the dissolved phosphates into particulate phosphates. So then they are converted into particles, and then they will be removed according to the previous particle removal mechanism. So if you can understand and remember these mechanisms, so you have come much far with understanding of the coagulation process. Right? So we talked about coagulants. There are many coagulants, and coagulation is not a new process. It's I think it was like 3,000 or 4,000 years before the crisis, Christus. People start to use coagulation because they understood that if you add some special chemicals like aluminium containing chemicals, they could see that the clarity of water changes. So the turbid waters, when they take it from the river because of sand, and they add some chemicals and they let it stay for, let's say, few hours, and then they see that all the particles are settled in the bottom, and they could take the topper amount or supernatant, which was clear. So from those years, aluminium salts have been functioning as the coagulant. So the most widely used coagulant is the aluminium sulfate, but we can also now find aluminium chlorides, aluminium nitrates, or any type of aluminium salt as coagulants. And then iron chlorides, iron Fe3, has been increasingly used because iron is cheaper than aluminium. But iron creates some other additional problems because iron has this yellowish color. Sometimes after treatment, the water will have this yellowish color, especially if you have too much iron added. And people don't like to have yellowish color, even in our, toilet basin. So we don't like to have, we would like to see the water is colorless, right? So the use is now reducing, and mostly iron is used for wastewater treatment. Calcium has been used for many years because calcium is the cheapest among these coagulants, but calcium has other problems. Calcium functions at higher pH levels, let's say pH 10, 11, but calcium precipitates everywhere. Right, so it creates problems. So if you have hard water, I guess Indonesia has hard water, and you have probably noticed that in your kettles, you get a coating of white calcium carbonates, right? And imagine in a treatment plant, so all the pipes, although you are not boiling water, calcium precipitates can occur everywhere, and it's a problem. So that's why we are very few treatment plants are using calcium now. It's also possible to use ferric or the ferrous sulfate, but 2-valent 2, but you have to convert into Fe3 before using it. But during the last 20, 30 years, number of new coagulants have come to the market. So the most popular one is called pre-polymerized coagulants. They could be pre-polymerized aluminium, which is the most common one, and we could also be pre-polymerized aluminium coagulants. So when we add aluminium or iron into water, the ultimate product will be aluminium hydroxide. But before coming to that stage, it goes through a number of stages. First, it will create an intermediate product of aluminium OH chlorine. So I should have had an equation here, I'm sorry. And then it's then aluminium and OH twice, and finally you come to aluminium OH thrice. But even that, it's not so simple. It goes through another maybe number of steps. So if the aluminium ion converts to hydroxides, then the mechanism for the particle removal will be the last one, sweep flock. But we have to utilize this positively charged species, and it can be improved if our coagulant is pre-polymerized. So this is the thought and logic behind that. And there has been some efforts to add silica and or water glass into coagulants, because when silica or the small sand particles are in the coagulants, the coagulant, the flocks will be constructed around the silica particles. So then the flocks will be heavier and they will settle fast. There were also coagulants with a combination of calcium, that means aluminium and iron coagulants, added with calcium. This is because that calcium functions with the first mechanism, the compression of the double layer. So in many wastewater treatment plants in Norway, for example, if they are situated along the coastline, so we add 5% or up to 8% seawater into our wastewater, because seawater has both calcium and magnesium, and then our coagulant demand will be reduced because of the double layer compression. So flocculants are special chemicals which make the flocculation process much faster, much better. So, but in practice, we have to first add coagulants and we have to add flocculants after that. It means that we have to have 2 chemical basins and 2 pumps. So here, there have been some attempts to prepare coagulants together with flocculants. It was functioning, but the biggest problem has been that they are not so stable. So after maybe 1 month or so, the coagulant starts to lose these properties. Chitosan is quite interesting. This is an organic polymer, and I think it's probably it's also quite relevant to Indonesia. Chitosan is produced from the shells of shrimps and crab. So there is no artificial chemicals. What you do is that you take the crab shells or the shrimp shells and you then boil it in acid and base, and then you get chitosan. First you get chitin and then you get chitosan. And when you produce chitosan, you're also getting rid of a problem, a solid waste problem created by shrimp waste and crab waste. The advantage of chitosan is that it is non-toxic, which is very good for drinking water treatment. And there are also new coagulants coming to the market, the titanium and zirconium based, because they have the 4th valency, they're much more efficient. But the downside is they are still too expensive because titanium and zirconium has other properties, other industries which are using, right? So if you know about titanium, it's quite light. It's used for airplane bodies and even for spectacles that to make them so lighter, you use titanium. Zirconium has other properties like for jewelries and different other things. So that's why they are still too expensive to use in drinking water. But I think it's changing. The things are changing. The world will soon start using them as well. Moringa. I hope that you recognize this word. Moringa is a vegetable used in Asia and Africa. I don't have a photo to show you, but these are these long vegetables, or the fruits, like not fruits, but long vegetables hanging in some trees. And inside there's a seed. And that seed could be dried and powdered, and then it functions as a coagulant. This is something which has been used in Asia and Africa for hundreds of years, because then you don't need to have aluminium, you can use Moringa. One of the biggest problems with aluminium is that if we have too much aluminium in the treated water, there is a potential to create a health impact. It is known that Alzheimer's disease, or the disease of senility, is created by, or could be created by, aluminium. And aluminium, iron, calcium, and phosphate, these 3 coagulants, they work in a very narrow coagulant range or pH range. But if you are working with Moringa or chitosan, they are not so dependent on the pH. So there are a lot of advantages and disadvantages. But aluminum and iron, they are cheap. They are so cheap, like we are talking about like $100 for a ton of aluminium. But if we talk about chitosan, it's still 10 to 100 times more expensive. So there are reasons why it is not so popular yet. Okay, so to sum up this first part of the lecture, here is a table showing what kind of chemicals we can use as coagulants and what mechanisms takes place. So we have the drinking water coagulation here, and here is the wastewater coagulant. And there are two types of coagulants, inorganic coagulants, that's aluminium, iron, and calcium. Organic coagulants, that could be organic polymers, polyacrylamide, or chitosan, or even Moringa. And the same with application in wastewater, the same two types. And then these are the four mechanisms: double layer compression, where we are compressing the double layer or the electron cloud. Adsorption charge neutralization, where we add positively charged species to neutralize the negatively charged particles. Third one is the interparticle bridging, adding polymers to bind these small particles in together. Finally, colloidal entrapment or seep flock, where the aluminum hydroxide and iron hydroxide precipitates. So in drinking water coagulation, the most dominant mechanism is the adsorption charge neutralization. But if we have organic polymers, then the interparticle bridging is the dominant mechanism. But even in drinking water, double layer compression occasionally happens and colloidal entrapment also happens, but you don't have to do it here, because if our drinking water process occurs here, means that we are not utilizing this part, means that we are wasting a little bit of coagulants. So in the wastewater, adsorption charge neutralization occurs frequently, but the dominant mechanism is colloidal entrapment or the sweep flow. For interparticle bridging, organic coagulants, it's always the dominant mechanism here. So you can then decide based on what kind of coagulant that you are using, whether it's inorganic or organic coagulant, and whether you are working in drinking water or wastewater, you can decide what mechanism is taking place most significantly. So during the coagulation process, we have three stages. First, we add chemicals, and we have to make sure that the chemicals are mixed extremely well. And this, because this hydrolysis process, it takes only seconds or parts of seconds to complete the reaction. So we have to make sure that the whole water volume is mixed with coagulants. After that, it goes to the flocculation stage. That means the smallest particles start to become growing, and they become like maybe 0.5 millimeter flocks, and after that 1, 2, 3, even maybe 3 to 5 millimeter big larger flocks. That's the flocculation stage. Finally, we have flocks and the purified water, and we have to separate them. So separation is, it could be sedimentation, flotation, or filtration, right? So now I have a couple of slides to show that how to design a flocculation stage. Flocculation stage means that you, after mixing of chemicals with water, and then these pinpoint flocks are starting, and we have to make sure that they grow as much as possible and as fast as possible. So there are definitions of how to define the mixing intensity. And it's one of the most common definition, or the factor we use is the G value. And there is how is described how to calculate that. I'm not going to detail into that. And there's also ways to decide that what should be the G value in the flocculation stage. If you have visited to a drinking water plant, you will see that usually there are a number of chambers for flocculation. It's not only one tank. So if you have 3 chambers, in the first one, the mixing intensity is quite high. That means the mixers, they go quite fast. And after that, it's a little bit slower, and the final one quite slow. So it means it gives the possibility for flocks to grow. And that you can calculate using the G value or the velocity gradient. And here is a slide showing the optimal dosages used in the drinking water and wastewater. So here is a simple equation for Norway. So when we know the color value in measured in milligram platina per liter, so we can multiply it by this figure and plus added this one, and then we get the aluminium dosage. But it could be different for different types of waters, depending on how much particles you have. In Norway, we have quite less low amount of particles. That's why we are focusing on color. So normal coagulant dosages, we are talking about 1.5 to 3 milligram aluminium per liter. PAX, polyaluminium chlorides, little bit higher. No, it's the same, but here you can see the difference of the pH ranges, and iron chloride is almost double the amount, right? So if you look at the wastewater situation, here we are adding a little bit more, and here you see that how the pH ranges are changing, and you can see that when we add iron, we add almost twice the amount of aluminium. Why is that? Why do you think that? Why do we have to add more more iron compared with aluminium? So if you remember the chemistry from your high school, you remember something called stoichiometry. That means chemical reactions, they do not happen according to the weight of chemicals you add, but it is based on the number of molecules. So one aluminium molecule react with 1 or 3 molecules of water or 1 molecule of phosphates. So if it is aluminium or iron, it's the same. So it's the same amount of molecules. And aluminium's molecular weight is 27 and iron molecular weight is 55 or 56. So that's why to add the same amount of molecules, you need to add double the amount of iron in weight. So this is the explanation for that. So I think with this slide, I will propose to have a small break. So let's take a break of 15 minutes. And after that, I will continue the lecture. Right?
Okay. Thank you very much, Professor Ratnaweera, for the interesting talks.